I want to consider a specific polynomial and then show that it is not solvable by radicals. So the polynomial I want to look at is p of x equals x to the fifth minus 13x squared plus 13, which belongs to the ring of polynomials with rational coefficients. And notice that it's irreducible by Eisenstein's irreducibility criterion with prime 13. Now, I want to show that this thing has at least 3 real roots, and I'm going to use the intermediate value theorem from Calc 1. I know, it's a real throwback. So I'm going to do a couple calculations here, and I'm going to do them without recording them because I am very prone to arithmetic error when doing things on the fly. So first of all, I noticed that when I plug in -1, I end up getting, all right, here's my first arithmetic error. I get -1, and that is less than 0. When I plug in 0, I get 13, and that's greater than 0. So that tells me there's a real root somewhere between -1 and 0. When I plug in 2, I get 32 minus 52 plus 13. That's 45 minus 52, and that's also less than 0. So that tells me I have another real root between 0 and 2. And when I plug in 3, I get 243 minus 117 plus 13, and that's greater than 0. So this tells me I have at least 3 real roots. By the intermediate value theorem, the good old IVT from Calc 1. Now, I want to also show that I have at most 3 real roots, so that I'm forced to have 2 complex roots. We'll see why soon. So I'm going to do some analysis with the first derivative to show where I'm increasing and decreasing. So let's take the derivative here. If I look at p prime, I'm going to get 5x to the fourth minus 26x. And let's see what's happening on these intervals between -1 and 0, 0 and 2, and 2 and 3. First, I want to let me factor out this 5x. So I get 5x, and then I have x cubed minus 26 fifths x, which is a little bit over 5. So it's just over 5x minus a little bit more than 5x. And when I say 5x, of course I'm lying because I factored out that x. So I get x cubed minus 26 fifths. And this allows us to find the critical values for x. So let's take a look at those critical values. That's where this derivative is 0. We're going to get x equals 0 and x equals the cube root, the real cube root here of 26 fifths. Okay, so let's do some first derivative tests to check out increasing and decreasing in here. So I already plugged in or we could plug in, let's say, -1 here, and we'd see that when x is less than 0, we have that p prime of x is positive. So we've got an increasing function when x is less than 0. When x is between 0 and the cube root of 26 fifths, we have only one of our factors is going to be negative, and that tells us that we have a decreasing function between 0 and the cube root of 26 fifths. And then when we look at what happens when x is greater than 26 fifths, both of our factors will be positive, cube root of 26 fifths, and that means that this is greater than 0. So this tells us that we're increasing, our function p of x is increasing, and when x is less than 0, it's decreasing when x is between 0 and the cube root of 26 fifths, which is, I guess, a little bit more than the cube root of 5, which is going to be, I don't know, cube root of 5, probably 1 and change. and then it's increasing again after when x is greater than the cube root of 26/5. The punchline from all of this is that we've got an increasing function, a function that goes from increasing to increasing again, which means that it can have at most 3 real roots depending on where those increasing and decreasing regions cross the axis. So this tells us at most 3 real roots. And so putting all of that information together, that tells us that p of x has 3 real roots, and I'm going to name them. I don't care what they are, I just need to know that they exist. Let's call them R1, R2, and R3. And that means that it has 2 complex roots by the fundamental theorem of algebra. And let's call those C1 and C2. So that's our old friend, the fundamental theorem of algebra from chapter 3, and then we saw him again in chapter 14. And back in chapter 3, we noted that if I've got 2 complex roots, C2 is going to be the conjugate of C1. So these are related by conjugation. And just to recap what the fundamental theorem of algebra says, that means that p of x is going to look like some constant, I don't know, let's call it k, times x minus r1, x minus r2, x minus r3, x minus c1, and x minus c2, which is c1 conjugate. So we know that our polynomial factors in this way. And now, if you've been paying attention, and I know you have because we've been checking in, the Galois group is going to tell us how we're allowed to switch around the roots of this polynomial p of x. Okay, time for our first proposition from chapter 28. This is proposition 28.1. It says that if we take p of x in q bracket x to be an irreducible of degree 5, if p of x has exactly 3 real roots, meaning 3 real roots and 2 complex roots, then the Galois group of q adjoin the roots of p of x over q is isomorphic to S5. And we know that that's going to be the end of our journey because we know that S5 is not a solvable group, which means the Galois group is not solvable, which means that p of x equals 0 isn't solvable by radicals. And that means that we can't have an algebraic quintic formula because we've got at least one quintic polynomial, we just saw it, that isn't solvable by radicals. Whew. So let's prove this proposition. This is going to be a romp through all the stuff that we have talked about this semester. Okay, so we're going to let R1, R2, and R3 be the real roots of p of x. And C1 and C2 be the complex, by which I mean not real, like legitimately complex. They've got an imaginary part. And we're gonna remind ourselves that C1 conjugate is C2 by proposition 3.12. So there is a look at something we did back in chapter 3. And I'm going to let G be the Galois group of Q adjoin the roots of P of X over Q, just to avoid writing that big long thing over and over. So G is my shorthand for the Galois group associated to the polynomial P of X. Okay, I should have mentioned up above that when I say exactly 3 real roots, I mean without repetition. So there are, by the fundamental theorem of algebra, that's proposition 14.2 in our book, this thing has exactly 5 roots, and so they're all distinct. The 5 roots are distinct. And that tells us that there's a one-to-one homomorphism and we've already looked at this guy. We've called him T. That goes from our Galois group G to S5. Why S5? Because we've got 5 roots. And if you want to remember what T does, T takes an automorphism in the Galois group and it sends it to the permutation it does to the roots. So it's F restricted to the roots R1, R2, R3, C1, and C2. So it takes an automorphism in our Galois group and it sends it to a permutation of the roots. And it's one-to-one. So I want to recall a few things about the way that this homomorphism of groups works. Remember that the image T of G, which is the image of T, is a subgroup of the codomain, which in this case is S5. And we already know that T is is one-to-one. That's how we built this function T. We know that T is injective, or one-to-one. So if we can show that T is also onto, then that means that T is an isomorphism of groups, and we finished proving the proposition. That would tell us that G, our Galois group, is isomorphic to S5, which is what we're trying to show. So that's what we're going to try to do. We're going to try to show that T is onto. And of course, we will succeed because this course is not designed around failure. Okay, by proposition 12.8, that's all of our vector space stuff coming back. We have that the dimension of the fields Q of P of X over Q adjoin R1 is finite. So we have a finite dimensional field here, and by proposition 12.4, we've got that Q adjoin R1 over Q is also finite. So what that tells us, the reason that we're doing this is I want to use the fact that the dimension of Q adjoin the roots of Px over Q is equal to the product of those two finite dimensions. So I've got Q adjoin the roots of Px over Q adjoin R1, and then Q adjoin R1 over Q. So this is also a finite dimensional vector space, and this is proposition 12.5. That says if you want to figure out the dimension, you can break it up into smaller pieces here. Okay, let's assume that P of X is monic. We may assume P of X is monic just by dividing through by the leading coefficient and worrying about it later. And the reason that I want to do this is oops, I forgot the word assume. We may assume P of X is monic, in which case it's the minimum polynomial of R1 over Q, right? It's an irreducible polynomial. R1 is a root, and as long as it's monic, it's the minimum polynomial. Now, even if it's not monic, we've got all of that stuff from understanding that f of x is a principal ideal domain. The irreducible polynomial is just going to end up being a multiple of p of x. So we can assume that p of x is it. It's not a big deal here. And that tells us that the dimension of Q adjoint R1 as a vector space over Q is 5. It's the degree of P of X. And that is from proposition 12.4 again. Okay, now, big shout out to Cauchy here. We'll see why in a second. What we just established is that 5 divides the order, or the dimension, of the vector space Q adjoin the roots of P of X over the field Q, which is equal to the size of our Galois group. And that is from a proposition, I didn't write down the number, but it's from a proposition where we talked about the dimensions of our vector spaces and how they relate to the size of our Galois groups. This is probably chapter 14 where we were counting automorphisms. And this is why we're excited. This means G has an element of order 5. Let's call that element G of order 5 by Cauchy's theorem. And what that means is that G to the 5th is the identity automorphism in our group. So G to the 5th is the identity. And no smaller power of G is going to be the identity. Now, since T is 1 to 1 by proposition 21.9, the order of this element T of G in S5 is going to be the order of, oops, let me get rid of that T. It's going to be the order of G, which is 5. So we just found an element of order 5 in the image of our automorphism. So the image of T contains an element of order 5. And remember that this image of T belongs to S5. So we found an element of order 5 in S5. By proposition 21.7, this element is a 5 cycle. Okay, so at this point we know that the image of T contains a 5 cycle. If we can show that it also contains a 2 cycle, we have a proposition that says S5 is generated by any 5 cycle and any 2 cycle, which means that the image of T has to be all of S5. At that point we're on to and we're done. So let's go hunting for that 2 cycle. Okay. The automorphism F from Q adjoin P of X to Q adjoin P of X via F of an element is its conjugate fixes Q. We've already seen that this is an automorphism. This is an example that we did in chapter 13. So this is a chapter 13 example. And that means that we have the conjugation automorphism in our Galois group. So F is an element of our Galois group, which we are naming G. And we also notice that for the real roots, F of anything real, like R1, R2, or R3, there's no imaginary part, so the conjugate is just the root itself for R1, R2, and R3. And F of C1 is C2, and F of C2 is C1. This means that T of F is the 2 cycle that sends C1 to C2, and it fixes R1, R2, and R3, and we know that this is a 2 cycle, so it's got order 2. Right? It's a 2 cycle. So T of F, wrong thing here. Let me, the image of T contains a 5 cycle and a 2 cycle, and therefore it contains whatever subgroup those things generate, right? S of our 5 cycle and our 2 cycle. Let's call the 5 cycle sigma and the 2 cycle tau. So S of sigma and tau. And that is all of S5, because S5 is generated by any 2 cycle and any 5 cycle. And that's proposition 19.9. All right, what that means is T is onto or surjective, as well as being injective, which is something that we learned earlier. Therefore, T is an isomorphism of groups. Thus, our Galois group, G, is isomorphic to S5. And that's what we wanted to show. So, what we can conclude is that P of x, the polynomial that we looked at earlier, x to the 5th minus 13x squared plus 13, is not solvable by radicals. And this provides an obstruction to an algebraic quintic formula. QE done, people. We did it. Thank you so much for a wonderful semester. I look forward to reading your final paper where you come up with your own quintic polynomial with similar calculus-flavored features. I get all emotional at this point in the year, and this is normally where I give you the big emotional goodbye speech, but I fear putting that on the internet forever so that everyone knows I actually do have a big heart. So let me just say it's been my pleasure having you in class this semester, and I hope to see you in person soon.